Today we're going to talk about using the intercept form for our quadratics. So as you can see, we're going to see something that looks like this, or we have our f of x is a x minus p times x minus q. So we've already graphed quadratic functions written in several different forms over the last few sections. The first one, the ax squared plus bx plus c. Remember, that is our standard form. And we talked about how we can create the axis of symmetry, the vertex, and all the rest of that to graph those. The second one, the g of x, this is the one that we just talked about, which is our vertex form. And then today we want to talk about this other form, which is called the intercept form. And as I just showed up above, it looks like a times x minus p times x minus q. In this form, the polynomial that's defined is in what we call factored form. So this actually gets back to what we did in the last chapter when we were factoring quadratics. And we're going to get them into that factored form. Remember, we used to talk about how you could find the solutions from factored form, because you could use the zero product property to make each of the binomials turn into equaling 0 to find the x-intercepts. So they were the solutions back in chapter 7, but now they're also going to be what we refer to as the intercepts of the graph. So obviously that's why we're calling this the intercept form, because it's going to help us find the intercepts. So in this form, the intercepts are actually p and q. Now notice we're seeing it in the form x minus p and x minus q. So if it's a minus on inside those binomials, it would be a positive p and positive q. If it was a plus p or a plus q, then obviously the number that went in had to be negative to turn it into the plus. So we want to keep that in mind as we go. So the axis of symmetry, we know, is halfway between our x-intercepts. So as you can kind of see on this little graph over to the side, we can see how the x-intercepts would be that same symmetrical equidistant from the axis of symmetry. So the axis of symmetry is going to be halfway between those x-intercepts. So the axis of symmetry, if you think about that, says basically we're going to take the p, add it to the q, and divide by 2. So basically, because it is halfway in between those 2 points, we're basically just going to find the average of those 2 points to find out where are they right down the middle. Now remember, when we see our graphs, they open up when our a value is greater than 0, and they open down when the a value is less than 0. So if it's a positive number, we know that it's opening upwards. If it's a negative number, we know it's opening downwards. And so what you have to also keep in mind is we still don't hear the word vertex. We're going to have to find the vertex. But remember, the vertex is the x-coordinate from our vertex comes from the axis of symmetry. So we'll have the x-coordinate of our vertex. We'll need to plug it into our quadratic to find what the y value is to match it, to find the vertex from there. But this is where we're going to hopefully, again, keep trying to speed up being able to graph without having to make a table of 5 points each time. So let's graph example 1. So we have a quadratic that's already been factored for us. It's in this intercept form. So a couple of quick things we want to do. We want to first notice that this is going to be something that is opening downward. That's for sure, because of that a value in front, which is a -1. So then we want to look at what are the intercepts of this factored form. Well, because this is x minus p, that means p has to be a -1. This x minus q, the q must be a 5. So because of that, I already have my x-intercepts for this graph. I have one of them being at -1 0 from that first binomial, and the second one is at 5, 0 from the second one. So I already have 2 points. So then I want to look at my axis of symmetry. So my axis of symmetry says add the p and the q, divide by 2, and that's going to give me the axis of symmetry. Well, -1 plus 5 is 4, divided by 2 is 2. So I know my axis of symmetry is at 2. So just to go one more step, to find my vertex, another important point in all of these, my vertex is going to be 2 from the x from the axis of symmetry, and I need to plug it into my function. So if I was to plug in a 2, if I plug in a 2 here, I'm going to get 2 plus 1 is 3. If I plug a 2 in here, I'm going to get a -3. So 3 times -3 is -9, times the -1 is now a +9. So I know my vertex is at 2, 9. So now we want to graph, get this onto our graph over here. So if I was to draw this line down, we're trying to get up to that 2, 9, which I'm not sure I'll quite make it, but we'll try. So the vertex is at 2, 9. So if I go over 2, 2, 4, 6, of course, there's about 2, 9. It's a little bit over. By my 2 intercepts, I have at -1, 0, and I have 5, 0 right there. Now we don't have our 4th and 5th points. I think at this point we've hopefully been graphing enough at this that we have an idea of what is happening. So we'll take this. Remember, we want to kind of round that top piece as best we can, and we're going to draw this down. We want to label our graph f of x. So there is the graph of the negative x plus 1 times x minus 5. Now, describe the domain and the range. So we've been doing this for quite some time this year now. The domain, still all real numbers. We don't have anything that's restricting what we can plug in. And our range this time, we have that highest point. Remember, the vertex, when it's opening downward, is the maximum. So that means we're going to have y values that are less than or equal to 9. So on this next example, there's actually a couple of ways you could solve this one without doing the factored form. You certainly could make a table, just start plugging in some x's to come out with some y's. You definitely could just solve this by moving the 8 over and dividing by 2, because you only have one term with x's in it. But I want to show you the factored form just to remind us how to factor, and just to see, because that's the section we're in. So remember, the very first thing we should be looking at in all of these is greatest common factor. So does 2x squared and 8 have a greatest common factor? Well, 2 is in both of them. So I definitely want to take out the 2's, which is going to leave me x squared minus 4. Now, when I think of x squared minus 4, what does that tell you? X squared minus 4, remember, is a dots pattern. That's the difference of 2 perfect squares. Remember, the difference of 2 perfect squares, the first term is a perfect square, which is x squared. The second term is also a perfect square, which is a 4, and it's always a difference. So remember, when we did this one, here was the pattern that we had to do. The 2 still stays there, but then we had x plus 2 and an x minus 2. So remember, there's a positive and a negative there. So now let's look at this, which is in factored form. So we know it's opening upwards because of the positive 2 in the front. We know that one of our intercepts is going to be at 2, 0. We know the other intercept is at -2, 0, because of the plus 2 and the -2. Then for our axis of symmetry, we're going to add those 2 together. We're going to get 2 plus -2, divide that by 2, which is 0. If I plugged in a 0 here, that will help me now find the vertex, we know that the x value of the vertex is a 0. If I plugged a 0 in, x squared is 0, times 2 is still 0, minus 8 is now the negative 8. So there I have 3 pretty important points. I'll label x-intercepts here so you can see those. Okay, so this time we're going to try to do opening up, and I'm going to try to put the x-axis way up here to try to get that negative 8 on my screen. We're at 0, negative 8. 2, 4, oh my goodness, 1, 2, 3, 4, 5, 6, 7, and again I missed it by 1, but there's my vertex at 0, negative 8. We have it at 2, 0, and negative 2, 0. Then I can draw my nice curved parabola opening upwards. This time we are labeling it just y equals 2x squared minus 8. Describing the domain and the range. Domain would be all real numbers. And this time my range, the lowest point in this when they opening up is the minimum value. The minimum value is at negative 8. So we're only going to see y values of negative 8 or greater. So next, remember we talked about how to find the zeros of a function. The zeros of a function are when the function's value, or the y, is 0. Not less than 0, it's 0. Okay, so when we talk about finding the zeros, that basically means when the function is equal to 0. So we can use this intercept form to help find the functions of the zeros very quickly. So here's an example on number 3. So it's already in the factored form. So in factored form, remember what we said was to find the zeros, that's when the f of x function is worth 0. So basically that is leading us into the factored form and using that zero product rule where we said if one of these is equal to 0, then the product would also make it 0. So if x minus 1 equals 0, I would add the 1 to both sides to say x equals 1. If x plus 2, I would subtract 2 from both sides, and it's now negative 2. So to find the zeros, these two answers are my zeros. They also, in this case, we're not asking for them to be this, but these are also, if I'm graphing, my x-intercepts, which should make sense because your x-intercepts have a y as a 0. So finding the zeros of a function, you can see them on a graph if you can see your x-intercepts, or if you can get them into factored form, you can set them equal to 0 to get to the two numbers. Okay? So next we want to talk about just finding some zeros here. When I would first look on this very first one, again, remember to think about greatest common factors. I can see a negative 2 in all of those terms. If I take out the negative 2, I get x squared. I get now a negative 5x, and I get a positive 6, and a positive 5x. Okay, remember, we have to make sure that these things all go back together. So I first had the negative 5x. You want to make sure you do a double check in your mind just to make sure that you're going to get back to where you started. So at this point, I still need to figure out what are my zeros, which is really when that function is worth 0. So thinking about my factor pairs that make 6, that would then add up to 5. Well, 2 and 3 would multiply together to get my 6. 2x plus 3x when I do my FOIL would give me the 5x. So here it is in factored form or intercept form. So if I was graphing this, my intercepts are sitting at negative 2 and negative 3. But in this case, we're looking for the zeros. So I just make the function worth 0. Now remember that negative 2 in the front, I would divide both sides by that negative 2, and 0 divided by negative 2 is going to become nothing or 0. So I really only have to focus on the x plus 2 equals 0 and the x plus 3 equals 0. X, when I subtract the negative 2, becomes a negative 2, and when I subtract the negative 3, I get x is negative 3. So my zeros of this function are at negative 2, negative 3. This next one, we just got to make sure we're careful. We want to make sure that we are really making all of our factored forms down as far as we can go. So when I do this one, there's nothing I can do to bring down x minus 1. That's as far as that one can go. But again, x squared minus 16, well, that's one of my dots patterns. So I would have my double bubble, x's are on the front, plus 4 minus 4. That's going to give me the 4x minus 4x that will disappear as the middle term, but the 4 times the negative 4 is negative 16. So this time, notice when I do my zeros, I have 3 binomials that are all different that I need to come up with my answers for. Okay, so this one is not just going to have 2 of my answers. So I'm going to have x minus 1 equals 0. If x plus 4 equals 0, it would work. And if x minus 4 equals 0, it would work. So if I add 1, x equals 1. If I subtract the 4, x's are negative 4. And if I add the 4, x is positive 4. So in this function, I actually have 3 answers. Negative 4, 1, and 4. So I'll have 3 different intercepts. This is actually something we call a cubic function. It actually is going to cross the x-axis 3 times and not just twice like a parabola would. On this next example, they're saying to use the zeros to graph. So again, just keeping in mind what that really means. The zeros are your x-intercepts. So I would use my factoring first to see if we can get this to factor. If I'm looking at x squared minus 2x minus 3, I know that I can do my factor pairs of 3, which are either 1 and negative 3 or negative 1 and positive 3, but I need a sum of a negative 2. So the first one is going to give me that sum of negative 2. The other one's going to give a positive 2. So if I then put in my double bubbles, I'm going to do x minus 1 and x plus 1 and x minus 3. So if I'm finding my intercepts or my zeros, my x-intercepts, it's going to be x plus 1, x minus 3. So x plus 1 equals 0, x minus 3 equals 0. I would subtract the 1, I would add the 3. So these are my zeros or my x-intercepts. So because of that, let's think about that. My axis of symmetry is going to be the 2 intercepts added together and then divided by 2. Negative 1 plus 3 is 2, divided by 2 is 1. So I know where my axis of symmetry is. The vertex, we also know that x is a 1. Now if I plug in 1 back up here into my function, 1 squared is 1, 2 times 1 is 2, 1 minus 2 is negative 1, minus 3 is negative 4. So there is the vertex. And then I just need to go and make my graph. There's my x and my y. My vertex is at 1, 1. Then I do negative 1. I go to my 3. And then I can draw my curve. And I get the graph. And that's the the intercept form. Again, it's helping you find the zeros of the function, which again are another way of saying the x-intercepts. We find our x-intercepts in the factored form. We know the axis of symmetry is halfway between our x-intercepts. And not too bad, but it's another way of showing us how to do that. Hope everything was easy on that. Let me know if you have any kind of questions and we can discuss it further.